Welcome to the second episode of Codeforces Slowrun series, where we look at a random 1300 rated problem from Codeforces and we brainstorm the ideas that are required to solve that problem. In this video, we will look at problem C, Permutation Partitions from Codeforces Global Round 7. This is a nice and easy problem, nothing too complex on the implementation side and also nothing too complex on the idea and brainstorming side. So let's talk about the problem statement. It says that you are given a permutation of length n. This means that all the integers are distinct and all the numbers from 1 to n they appear in the array. Then you have to split the original array of length n into k blocks such that every element is part of one block. And the size of the blocks could be anything, but the total number of blocks that you create, that should be equal to exactly k. So for example, if k is equal to 4, then you have to create these 4 blocks, and there could be multiple ways to create 4 blocks. You have to create the blocks in such a way that you maximize this quantity, which is the sum of the values in the block. That is, if your first block is of red color, then you look at all the elements inside this first block, you compute their maxima, and let's call that maxima as maxima of red. Then this would be maxima of blue, this would be maxima of green, and this would be maxima of white. Then you have to compute the sum of all the maximas from each block, and you have to split the blocks in an optimal way such that this maximum value is maximized. So this is the first question that you have to answer, and the second question that will be asked is, sure, you can split it to achieve this maximum, but how many ways are there to create such partitions where there are a total of k blocks such that in all of those partitions the maxima achieves this value, like maxima, sum of maxima is equal to the maximum possible value. So let's see how we can approach this problem. But before going to the next slide, you might want to pause this video and try out this problem for yourself. And if your rating is around 1300 to 1500, you should be able to solve this problem in, let's say, 5 to 10 minutes. It's not a difficult problem per se, but let's look at the idea. So assume that this is your array of length n, and you know that you will be splitting it into k blocks, right? Suppose this is the first block and this is the second block, this is the third block, and this is the fourth block. Let's say this is the fifth block. Then you can see that you have to add 5 quantities: first, second, third, fourth, and fifth. So you have to maximize this sum m maxima from this block. So that's why I will write maxima of color, where color belongs to white, red, blue, green, or yellow. Now you can see that there will be only a total of 5 terms because k is equal to 5 regardless of what n is. Now if I give you an array and I tell you that you have to split it into certain blocks and then take the maxima of each block, you will realize that maxima, whatever maxima you take, maxima should belong to the block, and not just that, it should also belong to the original array. So if there was no restriction, then just by looking at this fact that the maxima should belong to the original array, you can clearly see that if you want 5 elements from the original array, the maximum sum could be 5 into n, because n is the maximum value available in the array. If you want to generalize it, you can say something like, if there was no restriction, then you could have produced n into k. But you will know that there are restrictions because all the elements, there are no multiple copies of n that you can select for each block. So let's figure out where n would be located. So n could be present in any of these blocks. Suppose it is present in this block. So if n is present in this block, then when you compute the maxima, since n is the maxima of the entire array, the result would be n. So you can claim that the maxima of the green block is equal to n. Now if you had to pick k numbers to maximize their sum, but you cannot select a number once, what is the best case scenario that you can create? The best case scenario is that if you want to select k numbers, then the first number you will of course select the largest number, which is n, and after that the second largest, which is n minus 1, then the third largest, n minus 2, fourth largest, n minus 3, and so on. This means that if you look at this quantity n minus k plus 1, you can only have these many maximas in the best case scenario. But right now it's not clear whether we can achieve the maxima of one block equal to n and the maxima of the second block equal to n minus 1, and so on. Now let's see if this is the theoretical best that we could do. Can we actually achieve this scenario? So now you will notice that if the maxima n is present over here in this green block, then where is n minus 1 present? Because if you keep n minus 1 inside this green block, like let's say n minus 1 is also present inside this green block, then this green block can only contribute n. It cannot contribute n minus 1. It means that the next time you select the maxima from either of these blocks, it will be strictly less than n minus 1, and we don't want that. So then you can see a very clear strategy which is correct, and that strategy is you locate where the maximum element of the array is. So suppose n is located over here, you can simply assume that n is located over here. Let me just pull up the array. If n is located over here, then you can simply assign this as one single block so that it produces the highest maxima which you can achieve, which is n, and it does not affect any other elements. Then you locate where n minus 1 is. Suppose n minus 1 is located over here. This is n minus 1. So you create one single block over here, and this will produce, because you are allowed to create blocks of length 1. So this is one block, and n will go in its separate block, n minus 1 will also go in its separate block. Then you figure out where n minus 2 is. Suppose n minus 2 is located over here. So you create a entirely separate block for this element. Then you locate where n minus 3 is. Suppose n minus 3 is located over here. So you create a separate block for n minus 3. Then you can notice that since you have only created blocks of length 1, let's write that down. You only create blocks of length 1. It means that each block can contribute the best possible values that is achievable. That is, one of the blocks will contribute n, second will contribute n minus 1, then it will contribute n minus 2, and so on. So this was the theoretical upper bound for the maximum sum, and you can see that you can actually achieve it by adding one element in one box. But then the problem told you to split it into several blocks such that every element is part of some block. So how do you ensure that? Suppose k was equal to 4. So assume that k was equal to 4. Then you can see that you have already created these 4 blocks. But then these elements are not part of the block. But every element had to be part of some block. So in that case, what you can do is you can simply merge this element over here, and you can merge these two elements over here. They will create one big giant green block. So let me clarify what I'm trying to say. So this element is on its own in a separate block. Then you can see that if you color this in blue and you merge them together, the maxima will still remain this. Why? Because we have created the blocks in descending order of the values. This means that you have already placed all the elements from n to n minus k plus 1. So whatever element is remaining, no matter in which block it goes, it can never be the maxima. So that's why your logic does not change. Your logic for computing this sum, this does not change. Similarly, what do you do with these two elements? You simply merge them into the next available block. Then what do you do with this element? You merge this into the next available block. And what do you do with this element? You merge this into this block. So now you can see that the answer is simply summation of from n to n minus k plus 1. Because how many integers are there in this range? So n minus k plus 1 to n. How many integers are there? Let's count. So that will be equal to b minus a plus 1. So n minus n plus k minus 1 plus 1. So n and n cancel out, and this cancels out. So there are exactly k elements, meaning k blocks, and remaining elements can be merged inside a block. So now this was the easy part. I'm sure most of you might have already figured this out already. Now let's look at the other version of the problem. In this version, you just had to print the maximum sum. And maximum sum, you know that regardless of what the permutation is, you can actually achieve this entire sum. Now, how many ways are there to achieve this entire sum? Now, this part requires a little bit of thinking, but it's not that complex. So maybe try to pause the video and see how you can approach this. That is, how many ways are there to partition it into blocks such that their maximum such that maximas from each block, they contribute and create the highest sum. So we'll follow that same technique as before. Let's locate the highest element, which is n, and let's give it its own block. And for the second highest, we give it its own block. Suppose the third highest element is over here, we give it its own block. Now let's see what happens. If you ignore all of these elements, of course you will still get the maxima. So for the other elements, it does not matter where you merge it, because for this element, even if you extend this blue block over here, the contribution would still be same, because the yellow block will contribute whatever the first yellow colored element is, and blue block will contribute whatever the first blue colored element is, because we have placed it in a decreasing order. So if you look at these elements that are in between, if you look at these elements, so you can see that this element, it can either be merged on the left hand side or on the right hand side. So let's consider a general scenario where you have colored this block already while assigning integers from n to n minus k plus 1. You have colored this block in some color, and you have colored this block in some color. Then there will be some elements that are in between. So suppose you have 3, 4, and suppose you have total of 5 elements. Then one thing is for sure, since this and these are different blocks, then some of this will go on the left hand side and some will go on the right hand side. Now what are the possibilities? So the first possibility is that you either color everything in blue and you take it as part of your first block and your answer will not change because they are strictly less than the already placed maximas. This is one option. What is the second option? Second option is that you exclude one element and you let this element go to the green side. So you take 1, 2, 3, 4 blocks on the blue side and then you give this to the green element. What is the third option? You can take the first 3 elements on your end, which is the blue side, and you can give these 2 elements to the green side. Fourth option is you can take just 2 elements on your side and you can give the remaining elements to the green. And what is the next option? You can take only one element on your side and you can give all the remaining thing to the blue, to the green side. And what is the last option? You don't take anything on your side, you give everything to the green side. So you can see that once you decided how many boxes to take on the LHS. So once you have decided that you want to take X number of boxes in the prefix, then the suffix has no choice but to automatically be assigned to the green block on the right hand side. This means that the total number of choices for all of these elements combined is equal to, you can either decide to place 0 elements inside this blue block, or 1 element, or 2 element, or 3 element, or 4 element, or 5 element. So there are a total of 5 elements. So this is the maximum number of elements that you can place inside your blue block. Then you can see that this number of choices is equal to whatever the gap is between them. So it is actually equal to gap plus 1. Why this plus 1 is happening? Because you might decide to skip this entire gap altogether and you say that I don't want to consume any element from the right hand side, just give me elements from the left hand side. So this entire gap has gap plus 1 options of being distributed either to the left hand side or to the right hand side. Now what about the terminal elements? Let's look at the terminal elements. So if you have this, sorry, if you have colored it like so, and of course we are assuming that one of these would be n. Suppose this is n, then one of these would be n minus 1, one of these would be n minus 2, one of these would be n minus 3. Now what happens to the blocks on the left hand side? You will see that they do not have any choice because they have to be merged over here. Why? Because you cannot create a new partitions, because then the number of blocks would become strictly greater than k, which we don't want. And we already did the best that we could to achieve the maximum value. Similarly, what happens to the elements that are on the right hand side, the terminal elements, they also do not have any choice, but they will eventually get merged over here. And for all the elements in between, suppose there are g elements in between, g represents the gap, then there are g plus 1 choices to distribute these g elements on the left hand side versus on the right hand side. Why g plus 1 and why not 2 to the power g or something? Because it is contiguous. So once you have assigned one prefix to the left block, you have to assign this remaining prefix to the right block. So that's why the total number of ways to split it is g plus 1. And the same reasoning will also follow here. It will be equal to g prime plus 1. And then over here it will be g double prime plus 1, whatever the value of the gap is. And you can see that all the choices are independent. That is, no matter what merging you did on this section, if you can freely do the merging on this section without this affecting your decision. Why? Because these elements that are already colored as a single block, they are already the highest elements that can ever be possible. So no matter whether you do the merging from here or here, the maxima will not change. So that's why this gap cannot influence this gap. This gap cannot influence this gap. So your answer would simply be, answer is the product of gap plus 1. Gap plus 1. And we have to add a caveat that don't count terminal elements. Don't count terminal. Or you could even say something like, the answer is nothing but the product of internal gaps. So it is the product of internal gaps plus 1. This is the answer for finding out the number of ways in which you can create the blocks such that the sum of the maximas of each block is maximum. And what is the maximum sum? That is nothing but the sum of all integers from this range. So that's about it. The implementation for this is pretty straightforward. So that's why I'm not going to implement this idea in the video. But if you are watching this video, make sure to implement this solution by yourself, and make sure to think a bit about why this merging strategy works, because to me it looks very trivial, but again, if you are starting out in competitive programming, then for you it might not be obvious on why this merging strategy works, and why the total number of choices is g plus 1 and not 2 to the power g. So if you have any other questions about this, do let me know in the comment sections. Or if you have any feedback for the 1300 rated series, do let me know in the comment section if you want me to continue this series. So depending upon the traction that it gets, I might try to add more videos to this series. Thank you.